Okay, today we're going to talk about magnetic flux. Okay, magnetic flux. We have previously talked about electric flux, so let's go over that a little bit. Magnetic flux, by the way, is given by phi, capital Phi sub B is our, that's our symbol for magnetic flux. Well, we had electric flux earlier. And electric flux, okay, given by phi, and now we're going to put in a sub E on there. It was given by the integral of our electric field dotted with the area that it was passing through, which was really just counting the field lines that passed through an area. That's really all it was. It was just the concentration of electric field through the area. All right, so we had our electric field, and we'd have an area through that. Our electric field had charges that would go from positive charges to negative charges. And then our area, okay, let's say that's our area. Our area, the area vector that we're talking about is the normal vector to that area. Okay, usually given by A cross B or some, yeah, so that's vector A, okay, with that being our field. Okay, and so our phi then would just be, was going to be the amount of field that's passing through this particular area, and so you can tell it's a maximum if it'd be perpendicular, right? Because dot product is maximum when they're perpendicular, and if they're parallel, then it becomes 0 because there's no flux going through that area. And so I take that back. No. If the area itself is perpendicular to the field, then the area vector is parallel, and that's where your dot product is going to be maximum. That's E dot A, but our electric field, another way of thinking about it is it's the amount of flux per unit area. Is another way of looking at it. That's the strength of our field. Okay, it's the number of field lines per area. Well, magnetic field is very similar. Okay, here's our magnetic field. And around our magnetic field, okay, so around this area we have this magnetic field passing through. Yeah. And our magnetic field is very similar to the same thing. The flux is the amount of magnetic field lines passing through the area. And this one is, so our phi B, instead of being E dot A, is now B dot A. Okay, or okay, if we have a slightly changing area, if we have a varying surface, then it's the integral over that surface. Should be over the surface, right? Okay, well, no, field if it's not enclosed, okay, if we don't have a surface enclosed, then it's just like this. But if we do create a surface, okay, and so we've got that surface there and our front surface here, and that's going to be parallel to it. Okay, so now if we have our magnetic field flowing through a box, our flux now becomes, well, sort of. We still have the same amount of field going through the front surface and the back surface. And this field, so we now have this, this whole thing has a value to it. Okay, do you guys remember what B was? B was in units of? Teslas. This is a Tesla, and this is meters squared, right? Okay, so our new unit, we have this new unit, is called a Weber. Okay, it's a Weber, but it's named after Max Weber, who's a German dude, so it's Weber. So 1 Tesla meter squared is a Weber. Okay, if you want to go ahead and call it a Weber, that's okay. But another way of thinking of a Tesla is then a Weber. Yeah, it's Darth Weber, right? Okay, so it was Wayne and Darth that did the Wayne's World, and it was Darth Weber. Yeah, never mind. Okay, this would equal 1 Tesla is a Weber per meter squared. WB, right? Yes, WB here is the symbol for a Weber. Okay, because a W would be a what? Yes, a watt. It would be okay. So if we were to actually enclose, okay, our magnetic field, then we can do the similar simplification that we had earlier with the with our electric flux. We can do the same thing with magnetic flux, and that was Gauss's law. Gauss's law. We had Gauss's law for electric fields. Okay, where if we had a closed surface, our E dot dA was equal to our enclosed charge over epsilon naught. Okay, so essentially just how much charge do we have inside of our Gaussian surface. That's going to tell us how much field we have coming out. It's going to be dependent upon that. All right, so we have a similar formula for our magnetic flux. Okay, however, you can't really put a magnetic field completely within a surface. So this is over a magnetic. This is over through a loop. Is what we have our Gauss's law for. So we create what's called an Amperian loop, and as we go through this loop, this becomes B dot dA. All right. But if we have B dot dA for our wire here, because what causes magnetic fields? But it's a current. A current causes a magnetic field. So here's our current and our field around this current. So okay, so we're this way, thumbs that way. So we're going to curl in that direction around the wire. Okay, it's going to be the direction of our magnetic field. All of our field lines through here are. We can't really create an area where we have field lines leaving and not coming back. So whatever's leaving through our field is also coming back through our field. And so what happens here? Is that for a closed loop, I'm sorry, so across the surface, B dot dA is equal to 0. And this is our Gauss's law for magnetic flux. Okay, this is, okay, so let's write this. This is one of those memorize this equations. This is going to be very useful. That the magnetic flux through an area, okay, the field going through a particular area is equal to 0 if we choose the right area. Okay? And that's about it for the magnetic flux.